All right. We're recording. Cool. There we go. Okay. So I wanted to make sure I could record this lecture so that in case you needed to go back to it, there would be a recording. So we're looking at the Classkick from chapter 6 notes, and we're looking at the 6.1 summary slide. I've screenshotted in the summary from page 358 of your textbook that gives all the key terms, all of the relevant formulas that were covered. I'm not going to read through this, but I do want to point out two of those key terms: discrete random variable and continuous random variable. And I just want to make sure we understand the difference between those. They're both types of random variables. So first, let's talk about what's a random variable. A random variable takes numerical values that describe the outcomes of some chance process, right? So I think the key there is that it is random. So there has to be some sort of element of chance to the particular outcome of interest. And it's a variable, so it needs to be able to take on different values. There needs to be variation. So for example, in our class, if I asked how many siblings each of you have, like your number of siblings, there will be some naturally occurring random variation in that. Some of you will say 0 because you have no siblings. Some of you will say 1. Some of you will say 2, right? So the number of siblings, that particular outcome, that's due to the random process of humans having kids. And there's also variation in it. There isn't one single value that it can take on. It can take on many values. So when it comes to number of siblings, that's a really good example of a discrete random variable. So I'm going to get that example written down, and then I want to look at the definition of what a discrete random variable is. So number of siblings is an example of a discrete random variable. And looking at the definition, why is that? It has a fixed set of possible values with gaps between them. So there's a fixed set of numbers that the number of siblings, that variable, can take on, from 0 all the way up to whatever the max number of children is that a human has ever birthed on this planet Earth. And there are gaps between the values that it can take on: 0, 1, 2, 3. It can't take on the value between 2 and 3. You can't have 2.3 siblings, right? You can have whole number values of siblings, basically, from 0 up to really whatever that max number of children value is. And there's gaps between, so it is discrete in that sense. But continuous, look at the definition of continuous. That's a variable that can take on all values in some interval of numbers. So rather than having gaps, it's continuous along a number line, essentially. So some good examples of continuous random variables would be your weight, your height, your hand span. Your hand span is actually the distance from the end of your pinky all the way to your thumb in a straight line. And these are examples of continuous random variables because we could theoretically have like a super precise scale or a super precise yardstick or a ruler that can actually allow us to measure your weight, your height, your hand span out to many, many, many decimal places, right? We can keep getting more and more precise as long as we have an instrument that allows us to get that precise and to get that accurate. And that's why it's continuous. It's not like if I were to ask your height, it's not, I mean, I'm 5'2", so it's not like the next option after 5'2" is 5'3", right? No, there's heights between that. You know, there are people who aren't perfectly 5'2" and who aren't perfectly 5'3". They're going to fall somewhere in between those values. So continuous random variables, they don't have gaps because they can take on any value within the interval, and we can keep getting more and more precise out to more and more decimal places. So I just wanted to point out the difference between those two. All right, and now we're going to take a look at the a free response question from the 2012 test that actually gets at the concept of a probability distribution. So we are going to be looking at a random variable in this problem. And before we begin, let's just make sure that we all have the same definition of what a probability distribution is. So the probability distribution of a random variable gives its possible values, the values the variable can take on, and for some reason this word got cut off, and their probabilities. So once we get into this example, what you will see in part A of this free response, that table represents the probability distribution because we actually have the possible values that the variable takes on in the table, as well as the probabilities that those outcomes occur. So let's set up the problem. So a charity fundraiser has a spin the pointer game that uses the spinner like the one illustrated in the figure below. A donation of $2 is required to play the game. So in order to play, you must pay $2 to the charity. And then for each $2 donation, a player spins the pointer once and receives the amount of money indicated in the sector where the pointer lands on the wheel. So let's just take a look at the wheel for a second and look at the options here. So it looks like there are 6 sectors. If the pointer lands on one of those 6, you get $0. You don't win any money. So in effect, you've actually lost $2 to play the game because you had to pay $2 to play, and then you're getting $0 in return. All right. So the charity is pocketing $2 from you, and you lost some money. Another option, your spinner can land on the $1 sector. And it looks like there are 3 of those. So let's think about that scenario. You've paid $2 to play. If your pointer lands on a $1, you get $1 back, which is nice. You've still lost $1. At the same time, though, the charity, let's think about it from the charity's perspective. You gave the charity $2 to play. They gave you $1 in return. The charity has at least pocketed $1 from you. So the charity actually has made $1 from you in that case. Let's look at the final option. For the final option, just one sector there. If your spinner lands on that sector, you win $10. So now let's think about that case. You've paid $2 to play. They're giving you $10 in return. That means your net gain is $8. You won $8. But that means the charity has actually lost $8. So you've won money. They've actually lost $8 from their pot. All right. So really the green and the orange outcomes, those are good for the charity. Those are a way for the charity to make money off of these contributions. That one $10 sector though, that's how you make money. And you as the player, that's what's hooking you in and having you say, I know that I'm not going to actually make any money if I land on the $0 or the $1 sector, but if I land on that $10 sector, I actually am going to make some money. I got a 1 in 10 chance of making some money off this game. And that might entice you to play. So with that setup in mind, and also with this key piece here, the spinner has an equal probability of landing on each of the 10 sectors, all right? An equal probability of landing on any one of those 10. That's because it appears that they are equal size, and that is a fair spinner game. Let's look at the questions. So part A, let X represent the net contribution to the charity. Okay, that's really critical there. X is our random variable. It will represent the net contribution to the charity. So in this probability table, when we're looking at X and we're looking at these 3 values, this is from the perspective of the charity, not you as the player, but the charity itself, all right? So consider yourself right now. You're not a player of this game. You are running this game. You work for the charity, all right? And your goal is to pocket as much money as possible. Well, there are actually 3 outcomes for you as the person running this game on behalf of the charity. You can get $2 off of a player. You can get $1 off of a player. Or you as the charity can actually lose $8 to a player. Let's talk about how these 3 outcomes can occur, right? And remember, our probability distribution in this table is from the perspective of the net contribution to the charity. Let's relate it back to the spinner itself. $0 on the spinner. Let's say you land on $0. Let's think about what that means to the charity. If you land on $0, you as the player You paid 2 to play, right? You paid $2, but you landed on 0. So the net contribution, I don't know why that keeps doing that. The net contribution, there we go, to the charity is $2. Why is that? Because the player loses $2 to play. Okay, that's your first outcome. What's your next outcome? If the spinner lands on $1, let's think about that in terms of the net contribution to the charity. You paid 2 to play, you land on $1 on the sector, they give you $1 back. The charity still has one of your dollars though. So the net contribution to the charity is $1. And why is that? Well, the player paid 2, but got 1 back. The last piece of this, the last sector, if you land on $10 as the player, 10. Let's think about that. What's the net contribution to the charity? You paid 2 to play. They gave you $10 in return. So you've actually gained $8, but the charity has lost $8. So the net contribution to the charity is actually not really a contribution at all. The net contribution to the charity is a loss of $8. That's why there's a negative in front of the $8 in this probability distribution in the table, because it represents a loss to the charity. But the player gains $8. All right. Our table is from the perspective of the charity. With all of this in mind, let's finish filling in the table. So we've got our 3 different outcomes across the top row of the table. Now let's figure out what's the probability that each of those outcomes occurs, because that's what a probability distribution is. It tells you what all the possible outcomes are and what the probabilities of those outcomes are. So for the charity to get $2 off of a player, it appears that there are actually 6 ways that can happen, right? We had 6 sectors that were green. So the probability there is 6 out of 10, or 0.6. For the charity to net $1, there were 3 ways that could happen, 3 out of 10. And lastly, for the charity to net negative $8, so actually to lose $8, there was a 1 in 10 chance that that would happen. All right, so there's 3 different outcomes for any particular spin. Okay, so that's your probability distribution. Now we can use that distribution to answer part B. What is the expected value of the net contribution to the charity for one play of the game? So expected value, if you read 6.1 or you watched the videos during our asynchronous day, you learned that expected value is just an average. The notation for expected value, capital E of X, or you may see it as mu of X. And remember, mu is that Greek letter, and it stands for a population mean, all right? And that's what the expected value is. It's an average, it's a mean. It's a mean of basically our random variable over the long term, over many, many trials, many, many tries, many, many plays of the game in this case. Let's take a look at the formula for expected value. So this is actually the formula that you are given on the AP Stats exam, all right? It's right on the first page of the 6-page formula sheet. And so it tells you that to find the mean of a discrete random variable, and in the case of the spinner game, these are discrete random variables, or this is a discrete random variable with 3 possible outcomes, $2, $1, -$8, right? There's gaps between our potential outcomes, the values it can take on. So note the notation, right? So mu sub x or mu of x, e of x. Look at the formula. It looks scary, but if we break it down, it's not scary at all. Before we actually dive into what the formula means, let's pull back for a second and talk about how expected value is just an average. It's just a mean. Well, if that's the case, think back to your spinner. If we're looking to find the average of all potential outcomes of this spinner from the perspective of the net contribution of the charity, what we want to do is take up all our outcomes, add them together, and divide by the number of outcomes we have. So we have 2 plus 2 plus 2 plus 2 plus 2 plus 2. Why 6 2s? Because for that outcome of $2, there were 6 in 10 sectors that would yield that contribution. Plus 1, plus 1, plus 1. Why 3 1s? Because for an outcome of $1, there were 3 out of 10 sectors on the wheel that would get us that net contribution to the charity. And then lastly, -8. Why just a single -8? There was only one way that could happen. So I'm going to add all those things up, and I'm going to divide by the number of possible outcomes. There were 10. And if you pop that in your calculator, you'll actually see that the expected value of the net contribution to the charity is 70 cents, $0.70, 70 cents. Okay. Let's talk about what that means in context. The expected value is 70 cents. And this is where language is actually really important. Language, your precision in your language really matters. So in order to finish this question, in order to finish out question B, we actually have to interpret this expected value of 70 cents in the context of the problem. Okay, so here's what that means. If this game was played many, many times, ideally an infinite number of times, right? But if this game was played many, many times over the long term, on average, the charity will make 70 cents for each game played. Now, something to keep in mind is that winning 70 cents, like the charity netting 70 cents off of a player, that wasn't one of our original options. Remember what our original options were. The charity could get $2, $1, or they could actually lose $8. So our expected value actually is not an outcome that can occur in the game. What it means is that over all of these trials, over all of these games played, if the charity keeps getting more and more people to play, on average, they can expect to actually make 70 cents per player, 70 cents per game played. So actually, the way that they have this game structured, it makes sense for the charity because in the long term, they're actually going to make money, all right? Okay, but now let's talk about the formula that you're given because it looks scary, right? But it's not if we think about how we just calculated that 70 cents. We took an average. Look at this formula. You've got sigma notation. That's a sum, adding up a bunch of things, right? You've got x sub I. X sub I, that's all of the possible outcomes. There were 3 in this case, $2, $1, and -$8. And lastly, P of x sub I, that's the probability that an outcome occurs. And so what we do is we take a particular outcome, x sub I, we multiply it by the probability that that outcome occurs, and then we sum that, we add that up across all the potential outcomes. That's exactly what we did when we found the average. I'm just going to clean up this math a little bit and show you how the formula relates to the math that we just did right here. All right, that outcome of 2, how many times did that appear in the spinner? 6 times out of 10. So the outcome of 2 gets multiplied by the probability that it occurs, 6 over 10. I'm going to add to that an outcome of $1. How many times did that occur? 3 out of 10 times on the spinner. I'm taking the outcome of $1 and multiplying it by the probability it occurs. Lastly, I'm going to add in losing $8. How many ways does that occur? 1 in 10. Look at what I just wrote down. It is exactly the same thing as what I have written in blue above it, except it's a more concise, succinct way to express finding an average. What it entails is taking the outcome and multiplying by the probability it occurs. Then do it again. Take the outcome, multiply by the probability it occurs. Take the outcome, multiply by the probability it occurs, add them all up, take the sum. That's your expected value. All right, so we've interpreted it in context. We've talked about the formula. Let's look at the last question here, the standard deviation. All right, so we're asked, what's the standard deviation of the net contribution? Let's look at the formula first. So the formula for standard deviation also looks scary. It's not once you break it down. So let me show you how we would do this, and then I'll relate it to the formula. When we covered standard deviation like a long time ago, we said sigma sub x. That's our notation for standard deviation. All right. And when we were finding standard deviation, we said that the first thing we had to do was actually find just the straight up deviations, not standard deviation, but the deviations. And what the deviations entail are taking our outcomes and figuring out how far they are from the mean. So in our case, that's going to be taking an outcome of 2, subtracting the mean of 0.70 from it. And then we want to take the outcome of 1, subtract the mean of 0.70 from it. Then we want to take the mean of -8 and then we want to take the outcome of -8 and subtract the mean of 0.70 from it. Those are all of our deviations. 3 possible outcomes, 3 deviations. And we said an issue when you're finding deviations is that deviations can be positive or negative. So these outcomes can fall above the mean, like in the case of $2 and $1, or they can fall below the mean in the case of -$8. And that becomes problematic because when we're going to sum all of these things up to get the standard deviation, those positives and those negatives start to like cancel each other out. So we said, well, okay, there are 2 ways that we could handle that. We just want to turn all of these deviations into positive somehow, right? To capture their magnitude. In order to turn deviations positive, you could square them or take the absolute value. And as it turns out, it's actually better if you square them because on the back end, we know how to undo a square, right? You can take a square root. There's really no good way to undo absolute value. So we're going to put that absolute value to the side. We're going to square all these deviations. By squaring the deviations, it removes that issue of positive and negative deviations canceling each other out. Okay, well, in addition to these deviations, remember that the standard deviation has to take into account that some of these outcomes are more likely to occur than others. There were 6 sectors on the wheel that gave us that outcome of $2. So I actually need to multiply that squared deviation of 2 minus 0.70. I need to multiply that by the probability that it occurs. Same thing here. That deviation from $1 or of $1 from 70 cents is going to occur 3 out of 10 times. And lastly, that deviation for the negative $8 will occur 1 out of 10 times. So I'm taking the deviations, I'm squaring them, I'm multiplying by the probability that those outcomes occur, I'm adding them all together. So I've got to add all these up. Pretend this is on like one big long line, right? And then the very last thing is taking the square root of all of this. Like, boom, you got to take the square root. Why do we take the square root in the end? We have to undo those squares that we put on all those deviations previously. So we kind of exploded all of those deviations by squaring them. We got to bring them back down to size by square rooting. All right, let me write this a little more elegantly and all in one line. So probability being multiplied by the deviation squared. Add that to the next outcome. Add that to the next outcome. There you have it. This is how we're going to find the standard deviation of the net contribution, which actually turns out to be 2,934. That's actually $2 and about 93 cents. All right. It's in the same metric as our outcomes were, $2, $1, negative $8. Okay. Let's interpret in context what that means, and then let's relate it back to the formula that you're given on the exam. Okay, so in context, we found the standard deviation, but we have to put some language around it. Why do we care? What does it mean in the context of the problem? So for standard deviation, so make sure I get this right. Here we go. If the game was played many times, on average, we would expect the typical, remember this? The typical game's net contribution to fall $2 and roughly 93 cents above and below the mean of 70 cents. Okay, that's interpreting the standard deviation in context. Now that standard deviation, that's a pretty big swing, right? Your expected value is 70 cents. The typical game's net contribution for the charity could be about $3 above 70 cents, but also $3 below. So it could bring him in the green or bring him into the red. What do I mean by that? $3 above 70 cents, that would be a big gain. $3 below 70 cents, that would be a big loss. So we're seeing some big swings here in terms of the standard deviation. But ultimately, if the charity can get a lot of people to play this game, they're going to make money in the end, because we're going to see over time that mean net contribution of 70 cents, that's actually going to fall out. That's how the trials are going to turn out over time in the long run. Let me show you just one more time here the standard deviation formula. And I just want to point out why this should not be scary to you. You got your big square root. You've got your sum. We're adding up a bunch of things. What are we adding up? We're adding up deviations. You're taking an observed outcome, $2, $1, negative $8. You're subtracting mu sub x. You're subtracting the mean, the expected value of 70 cents. You're squaring those deviations, and then you're multiplying by the probability that that outcome occurs. And then you just do that for all the outcomes. Add them up, big square root at the end. right? That's the standard deviation formula. If you can figure out what's happening within the formula and remember the process by which we find standard deviation, that formula becomes a lot less scary in terms of getting to this point here. All right. So we did it. We lectured. I hope you enjoyed. I will see you guys next time. Adios, muchachos.